All right, now that we've learned a couple of things about exponential functions, we're now going to look at using exponential functions to model interest calculations for money and savings accounts. And we're going to look at how to use exponential functions to model growth rates in animal population or human population. So go ahead and pause the video, and I want you to take your notes, and I want you to write this function down that we're going to be using to model calculating interest rates for bank accounts and population. Okay, now that your notes are taken, let's take a look at what an exponential function growth factor and decay factor is. Well, B is just either a growth factor if it's bigger than 1, or it's the decay factor if it's between 0 and 1. And in our model over here, the B value that was in our previous exponential function is now what is in parentheses here, 1 plus R, where R is not our growth or decay factor, it is our growth or decay rate. How fast is our population growing or our money growing, or how fast is it decaying or decreasing over time? Okay, so let's take a look at using this model here. The value of this model, A of t, represents the amount of money or the amount of population that we have after a certain number of years. The initial population or the initial amount of money is this little A factor right here, this little A variable. Again, this R is our rate of growth or rate of decay. 1 plus R is our growth factor or decay factor. So I know that's a little confusing, but you're going to have to get those two terms straight. Our rate of growth is R for rate. Our growth factor or decay factor is this 1 plus R. And then this exponent right here is really our input value. If this is a function, this says that we're calculating this amount using t as our input value. And so this is really the x value that we saw in our previous exponential functions. So let's take a look at these two problems here and look at how we can use our model right here, our exponential growth or decay model, in order to calculate interest. So it says here that you invested $1,000 in a savings account at the end of 6th grade. This $1,000 is your initial amount. This is what you put in the bank. And it is our initial amount. And we put our initial amount into this little A factor when we calculate. So let's go ahead and start building our function. Our initial amount is going to go in for our little A value. Our initial amount is $1,000. And we put that in at the end of our 6th grade year. And it says the account pays 5% annual interest. So I know with a savings account, if I'm getting interest, my money is growing. So my growth rate is positive, and it is 5%. And how do you represent percent as a decimal? We take our percent, which is 5, and our decimal place here, and we move it to the left by 2. And that is our percent that we write in here for R. And R is always going to be a decimal, and it's not ever going to be written as a percent, but as the decimal form of a percent. And it says how much money will be in the bank account after 6 years. So the time that we're leaving it in our bank account is going to be 6 years. So when we go ahead and calculate that out, 1 plus 0.05 is 1.05, and you can see that this is our B value now. Our X value is 6, our B value is 1.05, and our initial value or A value is 1,000. How much money will we have after 6 years? This is where you guys are going to break your calculators out, because nobody's ever going to do this exponent without a calculator. So go ahead and break your calculators out and let's do the calculation. When I finish that calculation off, I get $1,340.10. And it's not an exact amount. I had to round, but that's how interest rates or interest is calculated. So after 6 years, I've earned. If I initially put in $1,000, I've earned $340.10 in interest after 6 years. So this is what is in my bank account after 6 years. So now let's go ahead and take a look at a population problem. And it says in this problem that in the year 2000, the number of Iberian lynx in the world was 150. And in the year 2004, the number decreased to 120. So instead of this being a growth problem, this is actually going to be a decay problem because my population is decreased over time. So how much has it decreased? Well, if we take a look at the decrease, it decreased by 30 lynx. So what is that number? What is that rate? If I put in, let's see, 30 over 150, what percent is that? Let's see, that's 3 over 15, which is 1/5. And I can calculate this in terms of a decimal. 1/5 is 0.2. Okay, or it actually decreased. That is a 20% decrease in population in just a year. That's horrible. But anyways, let's see how we can use this 0.2% to figure out how many Iberian lynx there will be in 2014. So let's build our function. We know that our initial amount of lynx was right here in the year 2003. That's when they first counted them. And we had 150 Iberian lynx. Since this is going to be a decrease, a decay function, we're not going to add our rate of growth. We're actually going to go ahead and subtract it because it is decreasing by 20%. So we're going to go ahead and say 1 minus 0.2. And how many years has passed since our initial year? If we take the year 2003 and subtract it from 2014, we get 11 years. 11 years later is what they really want us to calculate. So what are we looking at here? We have 150, and 1 minus 0.2 is 0.8, and we're going to raise that to the 11 power. And when we're done doing our calculations, again, you're going to go ahead and break out your calculator here. But when we're done doing our calculations, we're looking at approximately 13 Iberian lynx. And remember, when we were dealing with money, we can have parts of dollars, right? We know what cents are. We can have parts of dollars. But here, when we did our calculation, we came up with a decimal point after our whole number. And we cannot have a fractional Iberian lynx. So we need to round to the nearest whole number of Iberian lynx for our answer. We need to make sure that it makes sense. And that's how you use this model right here to model interest rates and to model population growths or decays.